Let me tell you about something that has sent shockwaves through the physics community, a warning from scientists who have spent their careers studying the cosmos, now confronting observations that shouldn't be possible. The James Webb Space Telescope, humanity's most powerful eye on the universe, has seen things that challenge the very foundations of our understanding. And some physicists are beginning to say what others are afraid to admit. Webb saw too much. Not too much in the sense of volume, though the data is vast, too much in the sense of impossibility. The telescope has observed structures, galaxies, and phenomena that our theories say cannot exist. Objects that formed too early, structures that grew too large, patterns that violate the timeline we thought we understood. When a leading physicist warns that we might be looking at a different universe than the one our theories describe, this is not hyperbole. This is not sensationalism. This is a sober assessment of what the data is telling us. And the data is telling us that something is profoundly wrong with our picture of cosmic history. I want to take you through what Webb has seen, why it's so disturbing, and what it might mean for our understanding of existence itself. Because this is not a minor adjustment to our models. This might be a revolution. Let me start with what Webb was designed to do. The James Webb Space Telescope launched on the 25th of December 2021 after decades of development and billions of dollars of investment. It is the largest and most powerful space telescope ever built with a primary mirror, 6.5 meters across more than 2.5 times the diameter of Hubble's mirror. Webb observes primarily in infrared light. This is crucial for its scientific mission because infrared allows Webb to see things that are invisible to optical telescopes like Hubble. First, infrared penetrates dust. The universe is filled with dust clouds that block visible light. Regions where stars are forming, galaxies shrouded in their own debris, cosmic nurseries hidden from optical view, all of these become visible in infrared. Second, infrared reveals the distant universe. Light from the most distant objects has been stretched by the expansion of the universe. What was once visible light has been shifted into infrared by the time it reaches us. To see the earliest galaxies, the first stars, the cosmic dawn, we must observe in infrared. Webb was designed to answer fundamental questions. When did the first stars form? When did the first galaxies assemble? How did the universe transition from the smooth, featureless state after the Big Bang to the complex, structured cosmos we see today? The telescope exceeded all expectations. Its mirrors aligned perfectly. Its sun shield deployed flawlessly. Its instruments performed better than specifications. Within months of beginning science operations, Webb was returning data of unprecedented quality, and that data contained surprises that no one anticipated. Now let me describe what Webb actually saw. The first shock came from the early universe observations. Webb peered back to when the universe was only a few 100 million years old, less than 5% of its current age. According to our models, this was supposed to be a primitive era. The first stars were just forming. The first galaxies were supposed to be small, irregular, and simple. Instead, Webb found mature galaxies, galaxies with hundreds of billions of stars, galaxies with well-defined spiral structures, galaxies with supermassive black holes at their centers, galaxies that looked like they had been evolving for billions of years but couldn't have been because the universe wasn't that old. The numbers were staggering. In the first deep field images, Webb detected galaxy candidates at redshifts of 10, 11, 12, and beyond. These correspond to times when the universe was 400 to 500 million years old. Some candidates appeared at redshifts suggesting ages of only 300 million years after the Big Bang. These weren't supposed to exist. Our models predicted that galaxies this massive, this mature, this well-organized would take billions of years to form. They should appear at redshifts of 2 or 3, not 10 or 12. They should be common in the recent universe, rare in the distant past, but Webb found them in abundance. Everywhere it looked. The second shock came from the sizes and masses. The early galaxies Webb detected weren't just unexpectedly present, they were unexpectedly massive. Some contained stellar masses comparable to the Milky Way. Some harbored black holes of billions of solar masses. This created what astronomers call the impossibly early galaxy problem. There simply wasn't enough time for these objects to form through the processes we understand. Consider how galaxies are supposed to form. After the Big Bang, matter was distributed almost uniformly. Tiny density fluctuations, regions slightly denser than average, gradually attracted more matter through gravity. Over hundreds of millions of years, these fluctuations grew into the first dark matter halos. Gas fell into these halos, cooled, and formed stars. The first stars were massive, short-lived, and explosive. They seeded the universe with heavy elements, enriching the gas from which later generations of stars would form. Galaxies grew through hierarchical assembly, small structures merging to form larger structures over billions of years. This process takes time. Gravity works at a finite speed. Gas must cool, collapse, and form stars. Stars must live and die. Mergers must occur. The timeline is constrained by physics. But Webb found galaxies that seemed to have skipped these steps. They appeared fully formed at times when they should have been embryonic. They contained stellar populations that should have required billions of years to accumulate in a universe that was only hundreds of millions of years old. The third shock came from the black holes. Supermassive black holes, the monsters at the centers of galaxies, millions to billions of times the mass of the sun, were supposed to grow slowly. A black hole forms when a massive star dies. It starts small, perhaps a few tens of solar masses. It grows by accreting matter, but accretion has limits. The Eddington limit describes the maximum rate at which a black hole can grow. If it accretes too fast, radiation pressure blows away the infalling matter. Even at the Eddington limit, growing a billion solar mass black hole takes time. Starting from a stellar mass seed, continuous maximum rate accretion for billions of years is required. But Webb found billion solar mass black holes in the early universe. Active galactic nuclei quasars powered by accreting supermassive black holes at redshifts where the universe was less than 1 billion years old. The math doesn't work. There wasn't enough time for these black holes to grow from stellar seeds. Either they started larger from heavy seeds that we don't understand, or they grew faster than the Eddington limit allows, which should be impossible, or our understanding of black hole physics is fundamentally wrong. The fourth shock came from the chemistry. The first generation of stars formed from primordial gas, hydrogen, and helium, the elements created in the Big Bang. These stars produced heavier elements through nuclear fusion and distributed them through supernovae. Only after this first generation lived and died could stars form from enriched gas. The signatures of this process should be visible in the earliest galaxies. The first galaxies should show low metallicity, few heavy elements, evidence of their primitive state. But Webb found surprisingly high metallicity in some early galaxies. The chemical enrichment was more advanced than expected. Stars had already lived and died in numbers that required more time than was available. This compounded the timeline problem. Not only were the galaxies too massive and too well organized, they were too chemically evolved. Every indicator pointed the same direction. These objects should not exist at the times where Webb found them. Now let me explain why these observations are so disturbing. The observations I've described don't just challenge details of our models. They challenge the foundation, the Lambda CDM model, the standard model of cosmology that has successfully explained observations for decades. Lambda CDM combines general relativity with assumptions about the universe's contents. About 5% ordinary matter, about 27% dark matter, about 68% dark energy, It describes how the universe expands, how structure forms, how galaxies assemble over cosmic time. Lambda CDM has been spectacularly successful. It explains the cosmic microwave background, the afterglow of the Big Bang, with remarkable precision. It explains the large-scale distribution of galaxies. It explains the expansion history of the universe. It has passed every test we've thrown at it until now. Webb's observations don't fit Lambda CDM. The early massive galaxies, the precocious black holes, the advanced chemistry, all of these violate the model's predictions. Either the observations are wrong or the model is wrong. The observations are probably not wrong. Webb's instruments are well calibrated. The data has been analyzed by multiple independent teams. The distances have been confirmed through spectroscopy. The galaxies are really there, really that early, really that massive. This leaves the model. Something about Lambda CDM must be incomplete or incorrect. This is why physicists are warning that we might be looking at a different universe. Not literally a different universe, the same stars, the same galaxies, the same physical space, but a universe that operates differently than we thought. A universe whose history unfolded differently than our theories describe. Now let me explore what might be wrong with our understanding. Several possibilities exist, and each has profound implications. The first possibility is that our understanding of star formation is wrong. Lambda CDM makes assumptions about how efficiently gas converts to stars. These assumptions are based on observations of nearby galaxies and detailed simulations. But if star formation was more efficient in the early universe, if gas converted to stars faster and more completely, then galaxies could grow massive more quickly, what might enhance early star formation? Perhaps the conditions were different. The early universe was denser, hotter, and more turbulent. Primordial gas had no heavy elements to cool it, but it also had no dust to impede collapse. Perhaps stars formed in massive bursts, converting most available gas to stars in short periods. Some simulations support this. Under certain conditions, star formation can be episodic and intense starbursts that briefly achieve efficiencies far higher than typical. If the early universe was dominated by such starbursts, the massive early galaxies might be explained. But this explanation has limits. Enhanced star formation can only do so much. Even at maximum efficiency, you can't form more stars than you have gas. And the gas must come from somewhere. It must fall into dark matter halos, which must themselves have formed. The timeline constraints remain. No matter how efficient star formation is, the underlying dark matter structures must exist first. And those structures are constrained by Lambda CDM. The second possibility is that our understanding of dark matter is wrong. Lambda CDM assumes that dark matter is cold, composed of heavy, slow-moving particles that clump efficiently. Cold dark matter produces a specific pattern of structure formation. Small halos form first, then merge to form larger halos over time. But what if dark matter isn't cold? What if it has properties that allow faster structure formation? Several alternatives have been proposed. Warm dark matter would suppress small-scale structure, but might behave differently on large scales. Self-interacting dark matter would allow halos to evolve differently than cold dark matter predicts. Dark matter with additional forces, a dark sector with its own interactions, could enable different formation pathways. Some of these alternatives might allow structures to form faster. If dark matter clumps more efficiently in the early universe, the scaffolding for galaxies would be available sooner. Galaxies could start forming earlier and reach massive sizes more quickly, but alternative dark matter models must also explain everything Lambda CDM explains. The cosmic microwave background, the galaxy distributions, the expansion history, any new model must match these observations while also explaining Webb's discoveries. This is a high bar. Lambda CDM wasn't chosen arbitrarily, it was selected because it fits the data. Alternative models that fit the new data often fail to fit the old data. Finding a model that explains everything is difficult. The third possibility is that our understanding of black hole formation is wrong. The massive early black holes might not have grown from stellar seeds. They might have formed differently from heavy seeds that started large. Several heavy seed mechanisms have been proposed. Direct collapse of massive gas clouds without passing through a stellar phase might create black holes of 10,000 to 100,000 solar masses. Collapse of the first generation of stars, if they were extremely massive, might create intermediate mass seeds. Mergers of stellar black holes in dense early environments might build up mass quickly. If heavy seeds were common in the early universe, the massive early black holes might be explained. Starting from a larger seed, less growth is required to reach 1 billion solar masses. The timeline becomes less constrained, but heavy seeds require special conditions. Direct collapse requires pristine gas with no metals to fragment it. Extreme stellar masses require unusual environments. Efficient mergers require dense stellar systems that might not have existed. We don't know if these conditions were common. We don't know if heavy seeds actually formed. The mechanism remains hypothetical, a solution to the problem rather than an observed phenomenon. The fourth possibility is that our understanding of the early universe is fundamentally wrong. Perhaps the Big Bang didn't happen exactly as we think. Perhaps the initial conditions were different. Perhaps the physics of the very early universe, the first fraction of a second, was different from what our theories describe. Inflation, the exponential expansion that supposedly occurred in the first instant, determines the initial fluctuations from which all structure grew. If inflation was different, if the fluctuations were larger on certain scales or had different statistical properties, structure formation could have proceeded differently. Some models predict features in the inflation-generated fluctuations, enhancements at particular scales that would seed early structure more efficiently. If such features exist and occur at the right scales, they might explain the early massive galaxies. But inflationary features are highly constrained by the cosmic microwave background. The CMB is exquisitely sensitive to the primordial fluctuations. Any significant features should be visible there. So far, the CMB shows no evidence of the features that would be required. The fifth possibility is the most radical. Perhaps our understanding of time, space, and cosmic history is fundamentally incomplete. Perhaps the universe is not what we think it is. This is what some physicists mean when they say it's a different universe. Not different in a trivial sense, different in a deep sense. Different physics, different history, different rules. This is a disturbing possibility. We have built our understanding of cosmology over a century, testing it against observations, refining it, extending it. The edifice seems solid. To suggest it might be wrong at a fundamental level is to question everything we think we know. But science requires honesty. If the observations don't fit the theory, we must consider that the theory might be wrong. This is how science progresses through confrontation with data that doesn't fit. Webb has provided that data. Now we must confront it. Now let me discuss what specific physicists have said. When I say that physicists are warning about a different universe, I'm not paraphrasing loosely. I'm reporting what researchers have actually said in papers, interviews, and conferences. Dr. Alison Kirkpatrick, an astrophysicist at the University of Kansas, expressed the sentiment directly when she examined the early Webb data. Looking at galaxies that shouldn't exist at the times where they were found, she and her colleagues confronted the possibility that their theoretical framework was wrong. Dr. Joel Leja of Penn State, analyzing the spectroscopic conformations of early massive galaxies, noted that the discoveries were challenging decades of established understanding. The galaxies weren't supposed to be there. The fact that they were required explanation. Dr. Garth Illingworth of UC Santa Cruz, a veteran of deep field astronomy who worked on the original Hubble deep fields, acknowledged that Webb was finding things that pushed the boundaries of theoretical models. The abundance and maturity of early galaxies was surprising even to those who had expected surprises. The community response has been a mixture of excitement and unease. Excitement because revolutions in understanding are rare and valuable. Unease because revolutions are also disruptive. They require abandoning comfortable frameworks and venturing into uncertainty. Some researchers have pushed back, arguing that the observations might be misinterpreted. Perhaps the distances are overestimated. Perhaps the masses are overestimated. Perhaps systematic errors in the analysis are creating apparent anomalies where none exist. These concerns are legitimate. Science requires skepticism. Extraordinary claims require extraordinary evidence, and the claims being made about Webb's discoveries are certainly extraordinary. But the evidence has held up. As more data has arrived, as more teams have analyzed it, as spectroscopic confirmations have accumulated, the anomalies have not gone away. If anything, they've become more robust. The scientific community is gradually accepting that something unexpected is happening. The question is no longer whether Webb found anomalies, but what those anomalies mean. Now let me explore the deeper implications. If our understanding of cosmic history is wrong, the implications extend far beyond astronomy. They touch on fundamental physics, on our understanding of time and space, on our conception of the universe and our place within it. Consider what Lambda CDM represents. It's not just a model of galaxies and expansion. It's a statement about the nature of reality. It says that the universe is governed by general relativity, that its contents are dark matter and dark energy and ordinary matter, that its history is a progression from hot and dense to cool and diffuse. If Lambda CDM is wrong, some of these statements might be wrong. Perhaps general relativity needs modification on cosmic scales. Perhaps dark matter and dark energy are different from what we assume. Perhaps the arrow of time, the direction of cosmic evolution, is more complex than a simple progression. These possibilities are speculative, but they're not impossible. Physics has undergone revolutions before. Newtonian gravity, once thought complete, was revealed as an approximation to general relativity. Classical physics, once thought complete, was revealed as an approximation to quantum mechanics. Each revolution preserved what worked while extending understanding into new domains. A cosmological revolution might do the same. Lambda CDM might be approximately correct on certain scales at certain times for certain observations while failing elsewhere. The task would be to find a more complete theory that encompasses Lambda CDM's successes while explaining its failures. This is how science advances, not by discarding everything, but by identifying what's incomplete and extending it. Webb's discoveries might be the catalyst for such an advance. Now let me reflect on what it means that Webb saw too much. The phrase Webb saw too much captures something important. It's not that Webb made errors or that the universe is hiding things. It's that Webb's power, its ability to see farther, clearer, and deeper than any previous telescope has revealed a universe richer and stranger than our theories prepared us for. This is the double-edged sword of observational progress. Better instruments reveal more, but more includes the unexpected. We build telescopes hoping to confirm our theories, but sometimes we refute them instead. Webb was supposed to confirm the broad outlines of cosmic history while filling in details. It was supposed to find the first galaxies and trace their evolution. It was supposed to validate Lambda CDM while refining its parameters. Instead, it found challenges. It found galaxies that shouldn't exist at the times where they exist. It found structures that formed too fast, black holes that grew too large, chemistry that evolved too quickly, Webb saw too much complexity, too much maturity, too much structure at times when simplicity was expected. This is uncomfortable. It means our understanding is wrong somewhere. It means we have work to do, observations to make, theories to revise, frameworks to rebuild. But it's also exciting. Comfort is the enemy of progress. A universe that matches our expectations teaches us nothing new. A universe that surprises us offers opportunities to learn. Webb has given us surprises. Now we must learn from them. In part 2, I want to explore the specific theoretical proposals being developed to explain Webb's observations. What new models are emerging? How might our understanding of cosmology change? And what further observations might distinguish between possibilities? So we've established what Webb has seen, the impossibly early galaxies, the precocious black holes, the advanced chemistry, and why these observations challenge our fundamental understanding. We've heard warnings from physicists that we might be looking at a different universe than our theories describe. Now I want to explore the theoretical responses. How are scientists attempting to explain what Webb has found? What new models are emerging? And what might these models tell us about the true nature of cosmic history? Let me begin by examining the theoretical landscape in more detail. The crisis created by Webb's observations has energized theoretical cosmology. Dozens of papers have been published proposing explanations, modifications, and alternatives. The field is in ferment, the kind of productive chaos that sometimes precedes major advances. The proposals fall into several categories, ranging from conservative adjustments to radical revisions. Let me work through them systematically. The first category involves modifying astrophysical assumptions. These proposals accept the basic framework of Lambda CDM, but argue that we've misunderstood some astrophysical processes. They don't challenge fundamental physics, they challenge our models of stars, galaxies, and black holes. One prominent proposal is super efficient early star formation. In standard models, only a fraction of available gas converts to stars. This efficiency varies with conditions, but it's typically 10% to 30% in star-forming regions. The rest of the gas remains unconverted, heated by stellar feedback, blown out by supernovae, or simply too diffuse to collapse. But what if early star formation was different? The early universe lacked the heavy elements that help gas cool and fragment. Counterintuitively, this might have made star formation more efficient, not less. Without fragmentation, gas clouds might have collapsed monolithically, converting a larger fraction to stars before feedback could disrupt them. Some simulations support this. Under pristine conditions, star formation can proceed with efficiencies approaching 100%, nearly all available gas converting to stars in rapid bursts. If this was common in the early universe, galaxies could accumulate stellar mass much faster than standard models assume. This proposal helps explain the massive early galaxies, but it has problems. High efficiency means high feedback, lots of supernovae, lots of energy injected into the surrounding gas. This feedback should suppress subsequent star formation, limiting total stellar mass. Balancing efficiency and feedback to produce massive galaxies remains challenging. Another proposal involves population 3 stars, the hypothetical first generation. Population 3 stars form from pristine primordial gas with no heavy elements. Theory suggests they were massive, perhaps hundreds of solar masses and short-lived, burning through their fuel in millions of years and exploding as supernovae. These massive stars would have been extraordinarily luminous. A galaxy containing many population 3 stars would appear brighter than its stellar mass alone would suggest. Perhaps the early galaxies Webb detected aren't as massive as they appear. Perhaps they contain relatively few extremely luminous stars rather than billions of ordinary stars. This could explain the brightness while relaxing the mass constraints, but spectroscopy doesn't support it. The spectra of Webb's early galaxies show signatures of evolved stellar populations, stars that have been through multiple generations, enriched with heavy elements. They don't look like population 3 dominated systems. Another astrophysical proposal involves active galactic nuclei, supermassive black holes, when actively accreting, can outshine their entire host galaxy. A small galaxy with a luminous central black hole might appear as massive as a large galaxy without one. Perhaps the early galaxies are smaller than they appear, their light dominated by central black holes rather than stars. This proposal has some support. Webb has found surprisingly many active galactic nuclei in the early universe, more than expected, with black holes that are massive relative to their host galaxies. Perhaps AGN contamination explains some of the anomalously bright early sources, but not all of them. Many early galaxies show no signs of AGN activity. Their light is clearly stellar, distributed across extended structures. The AGN explanation helps in some cases, but doesn't resolve the broader puzzle. The second category involves modifying dark matter properties. These proposals accept most of Lambda CDM, but change assumptions about dark matter. They argue that dark matter's properties affect structure formation in ways we haven't correctly modeled. One proposal involves fuzzy dark matter. Fuzzy dark matter consists of extremely light particles, so light that their quantum wavelengths are astronomical in scale. This fuzziness suppresses structure formation on small scales while preserving it on large scales. At first glance, this seems to make the problem worse. Suppressing small-scale structure should delay galaxy formation, not accelerate it. But some models suggest that fuzzy dark matter could enhance structure formation on intermediate scales, the scales relevant for early galaxy formation, while suppressing it on smaller scales. This is speculative, and the models are complex. Whether fuzzy dark matter can actually explain Webb's observations remains unclear. The proposal is being actively investigated. Another proposal involves self-interacting dark matter. Standard cold dark matter particles interact only through gravity. They pass through each other without scattering, accumulating in halos without ever colliding. But what if dark matter particles do interact with each other? Self-interactions would allow energy to transfer between particles, affecting how halos form and evolve. Cores would be softer, less concentrated. Halos might merge more efficiently, building mass faster. Some models suggest that self-interactions could accelerate early structure formation. By redistributing energy within halos, self-interactions might allow more rapid collapse and more efficient galaxy formation, but self-interacting dark matter is constrained by other observations. Galaxy clusters, gravitational lensing, and cosmic microwave background measurements all constrain dark matter properties. Any model that explains Webb's observations must also satisfy these constraints. Another proposal involves dark matter decay or annihilation. If dark matter particles can decay into other particles or annihilate, when they collide, they release energy. This energy could affect structure, formation, heating, gas, ionizing atoms, altering the conditions for galaxy formation. Some models propose that early dark matter annihilation provided an extra energy source that accelerated cosmic evolution. The additional energy might have enhanced star formation, powered early black hole growth, or altered the chemistry of the early universe. These models are exotic and poorly constrained. We don't know if dark matter decays or annihilates at rates that would matter, but the possibility is being explored. The third category involves modifying gravity. These proposals challenge general relativity, the theory of gravity that underlies Lambda CDM. They argue that gravity might behave differently on cosmic scales or at early times. Modified gravity theories have a long history. Modified Newtonian dynamics was proposed decades ago to explain galaxy rotation curves without dark matter. Relativistic extensions of MOND and other modified gravity theories have been developed to address cosmological observations. Could modified gravity explain Webb's observations? Some theorists argue yes. If gravity was stronger in the early universe, structures would have formed faster, density fluctuations would have collapsed more quickly, galaxies would have assembled earlier. But modifying gravity is dangerous. General relativity is one of the best tested theories in physics. It explains Mercury's orbit, gravitational lensing, gravitational waves, black holes, and the expansion of the universe. Any modification must preserve